In the last video, we set up a model, a mechanistic model, for describing the spread of disease. We took into account the fact that there were a couple of key events that lead to changes in the state of a system. We had people who are susceptible can become infected, and we had people who are infected who could recover. And based on that, we estimated the change in the number of susceptibles, the change in the number of infecteds, and the change in the number of recovereds, and wrote down a difference equation to describe that. Now, what I'd like to do in this video is talk about what that model actually predicts and see how we can use Octave to come up with a numerical solution for this system. Now, before we do that, what I want you to notice is that this equation is nonlinear. And it's nonlinear because we have terms like Sn times In. Actually, it's over n, which, if you recall, n was the population size. That was just S plus I plus R. So this is certainly not a linear system of equations. We don't have just constants multiplied by our unknowns, but rather we have products and quotients involving those unknowns. What that means is we're not going to be able to write this in matrix form. It's in a nice form like xn plus 1 equals axn plus b. That's not going to be an option. And that also means that an analytical solution is going to be very difficult to come by. It's not impossible under certain circumstances, but for the most part, for nonlinear equations like this, we cannot actually write down a nice formula that's going to tell us how to calculate the state variable at any given point in time. But we can still use a computer. And so I'm going to fire up Octave here. All right, so here's some code that I wrote, and we'll zoom in just a little so you can read that better. Couple of things. At the start, as usual, I like to start with a blank slate. So I'll clear all of my variables, I'll close all of my windows, and clear out the command history. And I'm going to make the font size a little bit larger so you can read. And then we'll start off by defining some parameters. And so here I'm defining a population size of 10,000. So we're going to imagine studying some sort of small town, like, say, Hillsdale, where the number of people is 10,000. We're going to use a single day as our time step, and we're going to define some parameters. Now, in this code, I used E instead of P for the transmission probability. Hopefully, that's not too confusing. If you want to change that in your notes and call it E, that's fine too. But I'm going to use a value of 0.01, meaning if you interact with someone who's sick, there's really only a very small chance that you're actually going to get sick, a 1 in 100 chance if you interact with a sick person. Secondly, we're going to use a contact rate of 25 per day. So we're going to assume that people interact with 25 other people. And notice, actually, E and C always show up together in our equations as being multiplied together. So the product of those two things is what matters. And so if you think that transmission probability is too low and the contact rate is too high, well, you can easily increase one and decrease the other, and you'll get essentially the same effect for the equations. Lastly, we have a recovery rate of 1/10, which means on average, this infection is going to last for 10 days. And again, you could easily change that parameter if you wanted to make the infection last longer or shorter. Okay, so with that in mind, let's go ahead and simulate this for 200 steps. And to help with that, I've defined the initial state. We're going to start with 10 people who are infected, and then everyone else is susceptible. No people are recovered. And I've created a function which takes in the values of S, I, and R and spits out the changes. So this function right here, you can think of as ds, change in S, di, and dr. It's the change in all three variables. Okay, and so you'll notice that's consistent with the model that we derived in the last video. So for our numerical solution, what we'll do is we will, first of all, create a matrix which has the first column as our initial state. And then from there on out, for shorthand, I'm going to use cur R for current R, cur I for current I, and current S as well to extract the last values of S, I, and R. And then we will plug those into the function f, calculate the new state, and go from there. Okay, and these conditional statements here, really not necessary, but every once in a while you'll find that when you're simulating a process like this, due to round off error, you can have some unexpected things happening. And so I've just put these in as a safeguard to say that if the number of infected people gets below 1, if we have less than 1 infected person, then that means nobody's sick. And so whatever decimal is left over, I'm going to put that in the recovered category. And then similarly, if we have less than 1 susceptible person, I'm going to put that in the infected category. So this is to take into account that we're actually allowing SI and R to be continuous variables, when in reality, they should come in whole number amounts. All right, but as far as the update rule goes, we're going to take our old state, which is column K. We're going to add the change, which was given by this function that we created before, and then we'll save that in a new column. And once that's complete, we can plot the results. And here I'm just plotting the row 1 in blue, row 2 in red, and row 3 in green. All right, well, let's run that and see what we get. And you notice we get a nice curve here. The susceptibles go down over time. So we started out with close to 10,000 susceptibles, but in the long run, it looks like somewhere around 1,000 people are susceptible. The recovered goes up over time, and it asymptotes to maybe around 9,000. And then the infecteds initially rises relatively quickly. It peaks at somewhere between 2,000 and 3,000, and then decays and goes back down to 0. And the reason for that is initially we had a lot of susceptible people. And so anytime somebody infected interacts with them, we're going to gain infected people. And so we're going to get exponential growth as a result. However, as the number of infected people grows, so does the number of recovered, and the number of susceptible people is dropping. And at some point, you'll find that there's really just not enough susceptible people to go around. And that's when the number of infected people peaks. And then we'll see that instead of the number of infected growing, it will start to shrink because slowly those people are going to start to recover. And so the rate of new infections slows over time due to the fact that the population of susceptibles is shrinking. And ultimately, it's surpassed by the recovery. And ultimately, we see the infected dies out and things return to normal. And in this particular model, it looks like most of the action happens in a 120 day span, so 3 or 4 months. And that seems like a very plausible timeline for an outbreak, comparable to what some of the models are predicting for COVID-19. All right, so there's the model. And let me just remind you what the actual data from a real epidemic looks like. So I'll switch over to my slides here, and you'll see that this graph this is again flu data from 2015 and 2016 flu season. It looks very, very similar, right? We had a very low number of infected people initially, an exponential rise, and then it peaks, and then it decays over a longer period of time. And so what's impressive about this is that a very simple model, which just took into account 2 different events, susceptibles and infecteds interacting, producing another infected, and then infected people recovering, that very simple model can actually capture this sort of trend. And if we were to actually try to match up the parameters of this model, we could potentially try to fit the model to this data. All right, so let me scroll ahead a couple of slides. By the way, the discussion in the slides doesn't match up exactly with this model. I threw some extra things into the notes, and so you can account for things like births and deaths as well as recoveries, and that's talked about in the slides. But for our purposes, we just focused on those 2 fundamental interactions because that's enough to reproduce the main behavior. But what I want to focus on now is what do you do next? Once you've got your model set up, even if you can solve it numerically, how do you actually apply this to data? And there are a few things that you can do. You can start by making some assumptions. Maybe you'll find that you have too many parameters and you won't know the values for all of them. So for example, in this simulation, we did not know the contact rate. We did not know the probability of infection. We did not know how long the infection was supposed to last. And so I just put some estimates in there. But ultimately, if you want to model some sort of real world system, it would be nice to be able to know more about that. And one thing you can do is you can just assume that some parameters are so small that we can safely ignore them. So as an example, I did not account for the fact that people could lose their immunity, that they could become susceptible again. And so in that simulation I just showed you, I left off the possibility of people transitioning from recovered to susceptible states. And I did that essentially by way of assuming that the immunity loss term was equal to 0. Okay, so we can make assumptions sometimes to reduce the number of parameters, and hopefully you'll have some empirical evidence to justify those sorts of assumptions. Secondly, you can use non-dimensionalization. So you had an extra credit homework assignment to look at, I believe it was chapter 9 or chapter 10, where they talk about non-dimensionalization. But what you'll often find is that there are certain parameters that really are kind of redundant or unnecessary. In this case, for example, notice we have EC that only shows up together. We don't have E and C separately. And so you could think of that as being just a single parameter. You could call it, say, beta, and set beta equal to EC, and that allows you to actually reduce the number of parameters that you need to estimate, right? It's still going to have this, the model is going to still have the same amount of flexibility, but it gives you one less parameter to keep track of. All right, the next thing you might do is try to use the data to estimate any other parameters. And one way to do that is you could compute, say, the difference between what you've predicted and what you actually observed, compute the sum of squared errors, and then use optimization to try to minimize that. So it would be a little bit tricky to find a nice exact function to compute the sum of squared errors here, because basically we had to run a simulation to get our predictions. But you could imagine writing a program that takes in parameters, E, C, L, and R are the parameters in this particular model, as well as the initial values. You could, with that program, spit out the values of S, I, and R at each point in time, and then try to tweak the parameters until you get those to match up. So although optimization can, in principle, be used, in practice more often, some sort of brute force searching for the optimal parameters is what people will do, or they'll use some sort of more intelligent method called something like perhaps gradient descent, which we may talk about later in the course if we have time. All right, so big picture, once you've proposed a mechanistic model, you may have many parameters that you don't know. And there are ways to use some of the optimization techniques we discussed earlier in the semester to fit those parameters. We won't make that a major focus right now, but some of you may find that on your projects, you may need to do that. And when the time comes, we can discuss the specifics of how you can actually optimize those parameters to get the best fit possible.